Hello everyone, welcome back to my class. In the previous session, we have seen the implementation details of the decorator design pattern, and there we have studied up to 3 issues. So we will continue with the 4th issue in this session, and we will look forward for the next topics as well as. Okay, so we will see the 4th issue of the decorator design pattern implementation details. Changing the skin of an object versus guts. So here in this point, changing the object's skin means that is nothing but the component design pattern what we are going to use, that is a decorator, it is going to use that object. Okay, so it is going to change the outline, right? So you will be having the text view component, the particular concept or a destination, you can tell, where it was actually in need of a designs. It should have some designs to it, so it requested for the design. So the decorator design pattern is going to provide the decorations for that component, right? So we are going to actually change the outlines. So we are going to give the functionalities for that one, right? So giving the functionalities like that, so it is nothing but changing the skin, so the outline, the skin, right? So in that meaning, so he has given changing the skin of a object. So it is going to add up the responsibilities, right? So while changing the skin of an object, or you can just he has given a guts. So guts are nothing but the internal thing how we are going to alter the contents for the components. So actually the strategy design pattern actually what it is going to do. So we are going to make use of the strategy design pattern in the definition, that is in the first module. So I have given a definition of the strategy design pattern actually, which is not in a syllabus. Let us recall the definition of this strategy design pattern. So it is going to use a strategy to select the complex algorithms required for the particular situation. In a strategy way means it is going to use the different kinds of notations or the different ways of choosing the algorithms. So it is going to use a strategy so to pick up the complex algorithms to solve the particular problems. So it is going to use that one. So we are going to use the strategy design pattern in combination with the decorator design pattern when you want to go with the that is the object guts changes. Okay, so how it is going to do, so I'll explain with the diagram. Okay, so I'll write up the diagram. you can just go through this diagram. So, here I have written components with the object creations there. So, you have got a decorator object and you have got that is another object that has been created to add functionalities for the component. You have got a component object. For that component you should have another object creation to add up the functionalities. That is this diagram we have seen in the previous motivation diagram itself, right. So, this part is no issues. So, here the decorator extended functionalities means the decorator is going to provide the functionalities. This is a one functionality, this is one functionality, and in the same way, so you can add up the extended functionality, so on. Okay. So, for the component. So, if you want to use the strategy design pattern in between this adding up the functionalities, so this will make like this. For example, you have a component. Okay, so within that you are going to use a strategies, that is using a strategy design pattern which will include or it will enclose the strategy design pattern. Within that it contains a next operation, that is it is going to have object that encloses another strategy. So, this I can tell extended strategy functionality. I can tell this part. Okay, so this follows like this. Actually, even I can add up one more box like a strategy, and I can include next. Okay, so here, so the complete operation you can go with the strategy based way. So, in a design pattern strategy, so which uses an efficient way to choose the complex algorithms. So, in order to add up the features, okay, instantly it is going to choose based on the situation, based on the problem conditions. So, you can actually go with this one. So, this issue it is going to tell us. So, how we are going to deal with the skin. Okay, so that is the skin, that is this one. So, the skin of a component object, and how we are going to deal with the guts of a component object. So, that is a difference. So, we are going to use strategy to deal with the guts of the object. Okay, so that is the means these are the few of the implementation issues that you need to consider in order to design the decorator design pattern. Now we will see that is sample code in order to write the decorator design pattern. Sample code to design the decorator. So, you can consider this code, this following code. So, the diagram code, it is going to shows how to implement user interface decorators in C++. Okay. So, we will assume there is a component class called visual component. Okay. So, we have used in the motivation also, right. So, we will assume it. So, we have got a visual component. Okay. So, that you can just see the coding part, class visual component. Okay. So, within that we have got public field. So, within that visual component method, and you have got void draw, so which is made as a virtual, and then you have got a resize. So, these operations will tell us, so that is I can draw that visual components, I can even resize the components. So, few of the operation he has included. So, that is you can just observe. So, it has been given with the dotted lines. So, even you can go with the some more operations included within that one. So, for a few as an example he has taken, that is a draw operation and the resize operations. Okay. So, we will see the next coding part. So, I will define subclass for visual component called the decorator. Okay. So, we will see how it is going to have obtain different decorations. So, class decorator, which is going to, that is inherit the visual component. Okay. Visual component was the base class. So and from there, so it is made as a public, so we are going to inherit all the public components from there. So you have got within a public field decorator. So within that it contains visual component, okay, so which is a pointer. So and then which contains a virtual void draw and the resize methods. These were already default in the visual component base class, okay, parent class, that was just derived, okay. So that follows, and then in a private section you can just see, so it contains visual component that is pointing to a component, means which is keeping a reference for the component object, okay. So the decorator decorates the visual component, okay. So the name of a class, that is a subclass decorator, it is going to decorate the visual component, okay, which is referenced by the underscore component instance variable, which is a reference variable which is initialized in the constructor. For each operation in visual components interface, decorator defines default implementation that passes the request on to underscore component, that is your instance variable. We'll see that one. So that is void decorator, okay. So that uses draw operation. So using the instance variable underscore, that is a component, so it is going to draw, and then same way for the resize operation it is going to call that instance variable, so that instance variable is, it is going to call that resize and it is going to work on it, okay. So in the same way actually you can go with the another derived classes, that is a class border decorator, and it will implement, or it is going to derive from the visual component base class. And the same way even you can go with a derived class, a scroll decorator, which will implement the visual component as a base class, and the procedure follows, okay. So that is a small pseudo code that we can keep for implementing the decorator design patterns. Now we will see the noun uses of the design pattern, that is uses. So this design pattern decorator, so can be used in all the C++ framework. So it is incorporated in the framework itself. Framework, so no need to mention the default uses, that is in a small talk, okay. So interviews is a name of application in object oriented environment, not your interview, okay. So small talk, interview, so in any of the C++ framework, so it makes or it finds it uses firstly in the C++ environment, okay. So as I discussed, the default thing will be small talk and the interviews, okay. So which is C++ based, okay. Next we will see the next uses in streams. Streams are nothing but basic abstraction interfaces for most of the input output operations. For example, you can accept the characters, numbers, ASCII characters and so on, right. So the input stream, output stream, what we are going to refer. So which is an abstract, okay. So it is going to accept all the kinds of input data. So there also we can use this design pattern. We will see how we are going to use with the diagram, okay. This is actually an example where you can find the usage of the decorator design pattern, that is in a streams. Okay, so input stream, output stream. So you have got so many streams, that is a memory stream, file stream, stream decorator. You have got to decorate this all kinds of streams. So ASCII stream, compressing stream. So you were actually not knowing, right? So there were so many kinds of streams present. Only we know input stream, output stream, right? So you can just see, so many types of streams are present in the computer system. So for each kinds of stream, if you want to design respectively, so you can use the decorator design pattern. So that is stream decorator is a design pattern here. So that is a decorator. So the same diagram, the diagram is it is going to remain same. So only thing we have written in terms of a stream. This may be the visual component, this may be the text view. Okay, so this may be another text view. So this is a decorator, this is scroll button, border button. Okay, the respective operations that is implemented. This diagram remains same, that is the area of application is different. So that is in a streams. Okay, so that is where you are going to find the usage of the decorator design pattern. So it is going to have for example memory stream. So it is going to handle the buffer full operations, means when the buffer is going to full, means you will be maintaining the buffer, right, in order to transfer the data, or means for the next for a period of some time, if you want to store the data temporarily, so you can use that buffer and so on. So when the buffer is filled, so you are going to use this mechanism. So some of the operations that can be implemented when the buffer is filled. So the same default operations will be carried to all of the components here. So that is ASCII files and then a stream decorator, compressing stream and so on. So the default operation is same for all the classes. So this is the noun uses of the decorator design patterns. Okay, so we'll see the next one. So that is next topic, related patterns of this decorator. Adapter, composite and strategy. So this three design patterns, that is the adapter, composite and the strategy design patterns, or the related patterns to this decorator. Okay, so this strategy already I explained, right? So using this strategy, actually you can give the better implementation for the object guards, right? So you can use this one. And this composite meaning itself tells, I told you, so the component it will be enclosed within a object itself. They might be there, the composite design pattern can be find its solutions, right? So there also you can go with this composite, and the adapter also, which is going to have interfaces implementations, right? So these three are the related patterns. Okay, so you can use according to the situations. Okay, so that is about the deep description about the decorator design pattern. Now we'll see the next design pattern, that is a facade. The next design pattern is a facade design pattern. So this design pattern, it is going to provide the unified interface for the subsystems. Okay, so and it is going to provide the efficient accessing traversing for the subsystems that underlays the facade design patterns. Okay, so means they will be having so many interfaces. So instead of so many interfaces that is interconnected with each other in the subsystem range, so it is going to provide a layer that is an interface layer. So below that it gives a channels for the subsystems. Okay, and through that unified interface, so it will give access to a main node and the sub nodes. Okay, so that is the meaning of this facade design pattern. So we'll see the intent section. And one more, that is facade defines higher level interface that makes easier to use subsystems. So we'll see the this intent section. So it is going to provide an interface, okay, which is an unified interface. Okay, so means unified means it contains branches. So for that branched one, it is going to provide one unified, means uniform interface. Okay, so unified interface to set of interfaces in a subsystem. So there is not only one interface in the subsystem, so is telling, so we have got set of interfaces in the subsystem. So now we have got so many interfaces in the subsystem. For those interfaces, this facade design pattern is going to provide a unified interface. Okay, so that is the first statement meaning. And the second one, so facade defines higher level interface. Okay, so it is going to provide the a bit higher level interface that makes easier to use the subsystems. So there might be so many subsystems present. Okay, so I don't know how to access that subsystem, or there may be problems in accessing the subsystems. So while designing the solution, so for the few of the implementations, so using few of the implementation, if you are designing the solutions and you are stuck, means you don't know how to access the subsystems. So there are so many subsystems. So I don't know how to access it, how to traverse it, and so on. So in that situation, you can use this facade design pattern, which will provide you the unified interface. Okay, so that is the intent section. So next we'll see the also known as there is no other name for this facade design pattern. No, not there, not present. Okay, only one name for the facade design pattern is, that is facade, no other names. Okay, so now we'll see the motivation behind using the facade design pattern. So that is why I need to use the facade design pattern. See, what happens, so when you are structuring the subsystems, okay, so actually it is going to reduce the complexity. So means when you have so many subsystems, so which has been interlinked with each other, so that will actually gives a good efficient one. So it is going to lessen the complexity, but you need to maintain neat communication between those. Means subsystems should be interconnected with each other, and there should not be any means connection erases, connection errors, like that. So interface connections error should not occur there. So actually the structuring of that subsystem is very helpful. So we can have so many subsystem design in one system only, right? So that will help us, but to maintain that is a difficult task. So you need to maintain means by providing the neat communications, okay. So means you need to keep in mind that minimize the dependency between the subsystems, and then the same that connections, the connection should also be minimized. So because the subsystem, what they are going to do, they are going to interconnect with each other. So we need to keep in mind, so that is the goal should be kept in our mind. So we need to minimize that one, so that connection, the communication should be minimized, and as well as there should not be any error regarding the dependencies between the subsystem. Means you should not have the dependency, one subsystem is dependent on the other subsystem, that should not be present, okay. So that is a 2 point you need to consider is less communication and dependencies. Dependencies will be there. I cannot tell that you should avoid the dependency, it is not possible. The subsystems are dependent on each other, but try to keep minimizing the dependencies and the connections, okay, communications. So that is the thing we need to consider. So if you consider this as a goal, okay, so if you consider this as a goal, it is a better option to choose facade design pattern in order to achieve this one. Okay, so this is a small definition. So a small definition where I can use this facade design pattern. So that is when you are having the goal to minimize the communication between the subsystem and to avoid the or minimize the dependencies between the subsystem, you can use this facade design pattern as a solution. Okay, so I'll write the abstract diagram, a small abstract diagram, so which will clear you the concept. So you can just go through this diagram. So if you understand this diagram, I think there is no need of explanation only. Okay. So diagram is very clear. So in the first diagram, you have got the client classes. So these boxes are nothing but the representation of a classes. Okay. So these are all the client classes I am going to take, and then here this section I am going to consider this as a subsystem classes, derived classes, which is derived from this class, which is derived from this one, and so on. Okay. These are all group of subsystems. Okay. So which are interconnected with each other, and you can just see they are actually dependent on each other. Okay. So it is clumsy actually, so very interconnected, so much of lots of communication may take place. Okay. So in the same diagram is represented here with slight changes. So that is, I have added our design pattern Facade. So you can just analyze the difference. Here in this client classes and the subsystem classes interface, I have given a design pattern called Facade. Okay. So if you want to get communicated with the subsystem, so use this Facade design pattern and communicate. So it is going to maintain the neat description of each and every subsystems that is going to be means underlying with the Facade design patterns, and it also contains the links to this client classes also, respective client classes. So which provides a neat unified interfaces for the set of, see here, set of interfaces. You have got so many interfaces here, and so many are there, no? So set of interfaces, for set of interfaces it is going to provide the unified interface. Okay. So that is the meaning, means how it is going to work actually. By looking at this diagram only, you can analyze how the Facade design pattern is going to work. Okay. So and he has taken an example of a compiler. Okay. So within a compiler you have got so many operation like parsing, semantics, syntax analyzer, like that. So you have got so much of classes that comes under the compiler, right? So that is basic compiler what you are going to use to compile your programming. So I am talking about that compiler. So that compiler contains so many subclasses. So how it is going to be interconnected, how it is going to allows that interconnection. So means in that compiler class is going to use this Facade design pattern. We will see that diagram. Consider this example. So that is a programming environment. Okay. So that gives the application access to its compiler subsystem. The subsystems contains like a scanner, parser, program node, bytecode stream, program node builder. Okay. So which is going to implement the compiler. Okay. So some of the specialized applications might need the access for these classes directly actually. But most clients, okay, so but most of the clients of a compiler generally don't care about details like parsing and code generation. They merely want to compile some code, right? So means we are not going to have the details of how the code is analyzed, how it is going to pass. I don't want to see those kinds of details. I just want my code to be compiled. So that is what the thing we need to focus. Okay. So for those kinds of people, the powerful and the low level interfaces in the compiler subsystem only complicate the task, right? So to provide an higher level interface that can shield the clients from these classes. Okay. So means the underlying classes will be there, no? So for example, so when you consider this as a compiler, okay, so that compiler, so it is going to include parser, code generator and so on like this. So the client may usually is going to have the access for all these kinds of things. So which is not actually required by the client. Parsing is not required to a user, and bytecode generator is not required to a user. So in order to overcome those things, okay, to hide those things, so you can use this Facade. So that is a compiler which is going to hide all the details of the subsystem, subclasses, that is a parsing class, syntax analyzer. So all these kinds of subclasses will be hidden in the compiler design pattern. Okay, so that is a design, that is a Facade design pattern. Within this compiler, so you will be having so many subclasses. Okay, so that is what the diagram is going to tell. The compiler class acts as a Facade. It offers clients a single simple interface to the compiler subsystem. It glues together the classes that implement compiler functionality without hiding them completely. The compiler Facade makes life easier for most programmers without hiding the lower level functionality from the few that needed it. Okay, so you can just go with this diagram. So the compiler is going to hide all the underlying classes, that is a subsystems that is going to work together with the compiler are hidden. Okay, so those are all not exposed to our clients using the Facade design pattern. Okay, so means we are going to hide all the subsystem interconnections, communication, dependencies, how they are actually inbuilt. So those part we are not exposing to our client. So that is about the motivation behind using the Facade design pattern. Stop here, we will continue in the next class. Thank you.